Welcome. Today we're going to talk about measuring the high side using our CS548 system. Let's get started. We'll be using a oscilloscope CS1096 current pulsar board. We'll measure the current using a CS1501 current sensing resistor connected to a CS1201 current digitizer. In addition, we'll be using the CS1133 Vsat probe to measure the saturation voltage across the transistor and a standard 100 times probe to measure VDS. Both of these measurements can be in the low or the high side. The CS1302 isolated digital 4-output, 1-input pod is used to drive the transistor. We use Pulse Builder to make the pulses. Here are all the connections. The CS548 is on the right and the CS1201 current probe on the left. Here are the wires as they're connected. VDS, channel A, ID goes to CS1201. VG logic tells us what the signal is that controls the gate, and Vsat is the saturation voltage. The CS1201 current digitizer is connected with fiber to the CS548. It has an adjustment to compensate for the CS1501 current sensor. The CS1096 switches the current. The CS1501 current sensor measures the high side current. The CS1133 Vsat probe measures the saturation voltage across the GaN transistor. The 10 times probe measures VDS across the transistor. And another 10 times probe is used to measure the gate drive logic level. And finally, a CS1301 isolated logic driver is used to control the gate. Let's get started on recording the CS1096 high side current measurement system. First of all, let's define the probes we've got. First one is VDS. The next one is current. Let's call it I, and it's actually in amps, so we'll make the units amps. The next one is the logic gate drive, so VG logic, and the last one is Vsat. Over here we've got 10 time probe on VDS, we've got a 1 time probe, but we're going to modify the gain on the current probe. We've got a 10 times probe on V logic, and we are using a Vsat probe CS1133 with the 1.5 volt setting. It has 3 settings. We'll use the 1.5 volt setting. Next, we have to make sure that the gain of the CS1201 is correct. We're going to use analog names in units. I've preset this value. What we've said here is that an input of 0 volts corresponds to 0 amps out. An input of 1 volt corresponds to minus 64.193 amps. I've calculated this using the resistor load value and the 80 volt swing that we're going to use in this experiment. It's quite simple to set values just by putting in pairs. This does gain and offset. I'll change the CS1201 internal channel to be remote. We're just waiting for the CS1201 to come online, and once it does, we're getting signals now. Now the next thing we need is a source of pulses, so we're going to use our Pulse Builder for that. So we go View, Pulse Builder. Now you'll notice on Pulse Builder we're using output 1 as the gate drive. That's all we need. I've set a 10 millisecond period, so it's running at 100 Hertz, 100 nanoseconds on, and then 100 nanoseconds off just to finish it off. Pulse Builder is not currently running. We can choose to use continuous output or single output. The number of iterations, start delay, you can see the values. I'll start it. Now currently Pulse Builder
is outputting this logic. Let's have some labels. So we'll turn all the labels on. And then we'll locate them. Let's move them somewhere useful. That looks like a good spot. Okay. Now in fact, I is actually ID, so I'll just put that in. So you'll see ID there, you'll see VDS here. It would be quite nice to have some more scales, so let's go and add an extra couple of scales on have 2 scales on each side. So now we've got V logic. There it is. It goes from 0 to about 5 volts. I'll just move that down a smidgen. And we've got ID and VDS. Now it's running off the Vsat probe power at the moment. Not very useful. I shall turn on the 80 volt power supply. I'll just move this down a tad. So here you can see the voltage, and it's around 80 volts. The current, and it's around 10.7 amps. We're only using 80 volts to excite it. We are using a 7.33 ohm load resistor with 80 volts. You can do the maths. It's around 10.7 amps. The tracer is currently on VDS, so I could measure VDS. If I put a marker on both of them, you can see it's 79.9 volts. If I hit the tab key, I go to the next channel, and I can see the current. You can see the tracer value following it. We can look at the flatness by use the keystroke 1 and the second keystroke 2 to place the markers, and it's pretty flat in the noise. If we want to improve things, we can do averaging. So the current is decaying by about 100 milliamps, probably because our storage caps on the power supply aren't quite big enough. The next channel is the logic drive, and so here we can measure the delay between the logic drive. Let's go from middle to middle. So there, I'll click 1. I can choose where to measure to by using the controls above the graph. So say I want to measure V to ID, I click on the ID and then go down here, and now the markers and tracer will be on ID. So I'll go 2. So now we can see the delay there is 22.64, but we also see that there is an error here because the CS1201 hasn't yet been time aligned. This is normally an automatic process, and we'll get round to it pretty quickly. But right now, let's do our manual time alignment. So we go to VDS, and we want to time align the centers of the 2 graphs. So that's about the center of VDS, and that's about the center of ID. We go up to Settings, Channel Time Alignment, and align M1 and M2. Now they're aligned. Now we can work out the delay more accurately. So let's go back to VLogic, and we can do that by clicking on this control and place a marker at the center point, 1, and going back to the current, there, and placing a marker there, 2. And we see the time delay through the gate drive and the actual device at 22.14 nanoseconds. Let's go and look at Vsat. This is Vsat, and you can see here there's an oscillatory period here where the capacitance of our silicon carbide diode is being dissipated. The diode itself has no storage charge, but it does have capacitance. It has to be dissipated. It takes about 15 nanoseconds. So from here on, Vsat is accurate. So we can see the change in voltage, and it's about 7 millivolts. I'm guessing that corresponds to the 100 milliamp change we saw. We could work it out based on the RdsOn of the FET. Now we'd like to derive some values, in particular power, energy and RdsOn. To do that, we open the maths equation builder and we start writing our equations. First of all, we want to calculate power, and power is voltage times current. In this case, current is channel B, ID. So we go B times D. D is the saturation voltage. And we send that to E, which we will use for power. Secondly, we want to calculate the integral of that. So we take E and we integrate it and we send it to F. And let's say F is the energy. Finally, we want to calculate RdsOn. And RdsOn is Vsat, D, over the current, B. And we could send that to G. But there'll be a problem. If the current is 0, which happens here, we'll have an infinity. So what we can do is, to get rid of that, we can use a conditional. So we go times greater than 0, and we'll use B minus 1. So if B, which is the current, is greater than 1 amp, then we run it. Otherwise we don't. We also need to integrate the energy. So we turn on the integral process and go apply equations. This sends these outputs to the maths graph. Let's fit the time on the maths graph, and we can see we've got some channels that need labeling. So let's start doing that. The first one is the power. So I'll go power, and it's in watts. The second one is energy. That's in joules. And the last is RdsOn. That's in ohms. We could add a few scales. So let's have VDS, ID and VG logic on one side, and have power, energy and RdsOn on the other side with 3 scales, Vsat sitting on the third scale, and we'll just have to choose between VLogic and Vsat, and we'll have 3 scales on each side. So now we have all the scales. We don't want VLogic, we want Vsat. So we click on this button to cycle through the available channels. The next is Vsat. So we have Vsat, ID and VDS. This makes it a bit easier to read. The labels are in the wrong position, so let's move them. That's not bad.
In line 3 of the maths equation builder, we calculate RdsOn and send it to channel G. You can see what the value is in channel G by using either the markers or the tracer. The markers show the value changes from 103 milliohms to about 104 milliohms. This can be logged using the signal information display logging system. We explain this later.
Energy is very small because it's in nanojoules, I'm guessing. So I'll choose the energy channel and I will use Control up to zoom in. You can see the energy axis changing. Now we could put a marker on either side. That's the total energy of this pulse, which you can see it's still running 1237 nanojoules. Multiply that by 100, because we're only going at 100 times per second, and that's the total joules per second, which is the total watts dissipated by the system. I thought I'd introduce you to the signal information window and logging. Here's the window. It shows you the labels for each channel and the parameters for that channel. We can set the information source to maths. Now the signal information will record derived values as well as real values. We scroll backwards and forwards to see the different channels. So I'm interested in up to RdsOn. We can actually show more channels as well if we want to, but 4 will do for now. Here we can see the power, the energy, and RdsOn. I also have, of course, these 2 markers here. Notice that I can measure just between the markers, so I'll do that now. I'll set the markers so that we just capture the portion of the graph where everything is stable. Marker 1 there and marker 2 there. Now the DC value will now correspond to each of the values except for the energy, which is between markers 1 and 2. So let's turn on logging, and we can log the channels we want to log down here, and we want to log E, F and G, for example, and also VDS, that's channel A, and the current, channel B, and let's also log the saturation voltage, which is D, and we'll log the DC value. Let's start. Now I'm going to reduce the voltage of our power supply. So I'm going past 50 now. And I've gone all the way down to 18. Now I can stop logging. I can find the log file by looking in Window, Open Cleverscope User Directory, and we're in captures, and it's defaulted to cscope log.txt. There it is there. Now for OpenXL, by just dragging it in, here you can see, I'll just widen this up a bit. You can see the time we captured, the offsets and gains, and then each of these values for all the channels A, B, D, E, F and G. And we can plot this if we wanted to. You can see all the values we captured. So you can quite easily extract these values and then use them for your own purposes. So this is how you do logging, and we've had a fairly good look at scaling, using the markers, using the scales, using the maths equation builders, and of course the 1201 and the CS1302 digital outputs driven by Pulse Builder.